What is a crystal oscillator, and what it components? A crystal oscillator is an electronic oscillator circuit that utilizes the mechanical resonance of a vibrating crystal of piezoelectric material to create an electrical signal with a very precise frequency. These oscillators are commonly used in various electronic devices such as computers, radios, televisions, and cell phones to provide stable and accurate timing signals. Here's a breakdown of key aspects of crystal oscillators. A crystal resonator is a key component of crystal oscillator circuits, providing the fundamental frequency reference for the oscillator's operation. It is typically made of a piezoelectric material, with quartz being the most common choice due to its excellent stability and predictable characteristics. Key points. Piezoelectric material. Quartz is the most widely used material for crystal resonators due to its exceptional piezoelectric properties. Other materials like lithium niobate, LiNBO3, and langasite, La3Ga5CO4, are also used in specialized applications. Physical structure. A crystal resonator is typically a thin piece of quartz crystal cut in a precise orientation to exhibit piezoelectric behavior. The most common cut is the AT cut, which provides good frequency stability over a wide temperature range. The crystal may be shaped into various forms such as plates, wafers, or tuning fork structures, depending on the application requirements. Resonant frequency. The resonant frequency of a crystal resonator is primarily determined by its physical dimensions, crystal cut, and the characteristics of the piezoelectric material. Quartz crystals can resonate at frequencies ranging from a few kilohertz to hundreds of megahertz, depending on their size and cut. Temperature stability. Quartz crystal resonators exhibit excellent temperature stability, making them suitable for applications requiring precise timing over a wide temperature range. Temperature-compensated crystal oscillators, TCXOs, and oven-controlled crystal oscillators, OCXOs, further enhance stability by actively controlling the crystal's temperature. Frequency tolerance and aging. Crystal resonators have tight frequency tolerances, typically specified in parts per million, ppm, or fractions of hertz. Although crystals are highly stable, they may experience slight frequency drift over time due to aging effects, which can be minimized through careful selection and aging processes during manufacturing. Mode of operation. Crystal resonators operate in various modes, with the most common being the fundamental mode and overtone modes. In the fundamental mode, the crystal vibrates at its fundamental resonant frequency. Overtone modes allow the crystal to resonate at harmonics of the fundamental frequency, enabling higher frequency operation. Crystal resonators serve as the heart of crystal oscillator circuits, providing stable and accurate timing references for a wide range of applications, including communication systems, digital devices, instrumentation, and precision timing equipment. Their precise frequency control and stability make them indispensable in modern electronics. The feedback circuit in a crystal oscillator is an essential component responsible for sustaining the oscillations generated by the crystal resonator. It ensures that a portion of the oscillator's output signal is fed back to its input in the correct phase and magnitude, creating a closed-loop system that maintains stable and accurate oscillations. Key points. Purpose. The primary purpose of the feedback circuit is to provide the necessary phase and amplitude correction to sustain oscillations at the desired frequency. It controls the feedback loop, ensuring that the output signal reinforces the input signal to maintain continuous oscillations. Components. Amplifier. The amplifier in the feedback circuit boosts the weak output signal from the crystal resonator to ensure that it has sufficient amplitude to sustain oscillations. The amplifier may also provide buffering to isolate the oscillator from external loads and maintain stability. Phase shifter. Some oscillator circuits may include phase shifting networks to ensure that the feedback signal is in phase with the input signal, which is crucial for stable oscillation. Filtering elements. Filters may be incorporated to suppress unwanted harmonics or noise in the oscillator's output signal, ensuring that only the desired frequency component is fed back to the input. Biasing components. Resistors, capacitors, and biasing networks provide the necessary biasing and stabilization for the active elements in the feedback circuit, such as transistors or operational amplifiers. Feedback path. The feedback path establishes the route through which a portion of the oscillator's output signal is fed back to its input. It typically consists of passive and active components arranged in a manner that maintains the correct phase relationship between the input and output signals. Stability and control. The design of the feedback circuit is crucial for ensuring the stability and performance of the oscillator. Parameters such as gain margin, phase margin, and loop bandwidth are carefully controlled to prevent instability, frequency drift, or unwanted oscillations. Types of oscillator circuits. Various oscillator topologies utilize different feedback circuits, including Pierce oscillator, commonly used in crystal oscillator circuits, featuring an inverting amplifier and capacitive feedback. Colpitts oscillator utilizes a capacitive voltage divider for feedback, often used in LC oscillators. Hartley oscillator employs an inductive voltage divider for feedback, also used in LC oscillators. Wien bridge oscillator uses a bridge network and operational amplifiers for feedback, commonly used in audio frequency oscillators. Frequency adjustment. Some oscillator circuits may include provisions for frequency adjustment or tuning, allowing the oscillator's frequency to be finely adjusted to meet specific requirements. This adjustment may be achieved by varying component values or applying external control signals. The feedback circuit plays a critical role in ensuring the stability, accuracy, and reliability of crystal oscillator circuits, making it a fundamental component in electronic devices requiring precise timing references. In the context of a crystal oscillator circuit, the amplifier plays a crucial role in boosting the weak output signal generated by the crystal resonator to a level sufficient for sustaining oscillations. It amplifies the signal while ensuring that it remains in phase with the input signal, thus facilitating stable oscillations. Key points. Function. The amplifier amplifies the oscillating signal produced by the crystal resonator to compensate for any losses in the feedback loop and ensure that the signal remains strong enough to sustain oscillations. It provides gain to overcome the inherent losses in the oscillator circuit and maintain the loop gain necessary for sustained oscillation. Types. Transistor amplifiers, bipolar junction transistors, BJTs, or field effect transistors, FETs, are commonly used as amplifiers in oscillator circuits. They provide high gain and can operate across a wide frequency range. Operational amplifiers, op-amps can be used as amplifiers in oscillator circuits, especially in Wien bridge or phase shift oscillator topologies. They offer high gain, low distortion, and good frequency response. Differential amplifiers. In some oscillator configurations, differential amplifiers may be employed to amplify the differential signal produced by the crystal resonator, providing better noise rejection and stability. Configuration. Amplifiers in oscillator circuits are typically configured as voltage amplifiers, where the input signal from the crystal resonator is amplified to produce an output signal with increased voltage magnitude. The amplifier may be configured as an inverting or non-inverting amplifier, depending on the specific oscillator topology and phase requirements. Biasing. Proper biasing of the amplifier is essential to ensure its stable and linear operation. Biasing circuits provide the necessary DC operating conditions for the amplifier, such as bias current or voltage. Biasing ensures that the amplifier operates within its linear region and minimizes distortion in the amplified signal. Frequency response. The amplifier's frequency response must be sufficient to cover the desired operating frequency range of the oscillator circuit. High-frequency amplifiers with wide bandwidth are preferred for oscillator applications to ensure that the amplifier can accurately amplify signals across the oscillator's frequency range. Stability. Amplifier stability is critical for the overall stability of the oscillator circuit. Proper compensation techniques, such as pole zero cancellation or frequency compensation, may be employed to ensure stability and prevent oscillations or instability in the amplifier. Output stage. In addition to amplification, the amplifier may also include an output stage to drive the load impedance and provide the required output signal amplitude. Output stages may include impedance matching networks or buffer stages to ensure efficient transfer of the amplified signal to the load. Overall, the amplifier in a crystal oscillator circuit plays a vital role in providing the necessary gain and stability to sustain oscillations generated by the crystal resonator, making it a key component in electronic devices requiring precise timing references. Frequency-determining components are key elements in oscillator circuits that establish the oscillation frequency. In a crystal oscillator, These components, along with the crystal resonator, set the precise frequency of the oscillator's output signal. The frequency-determining components primarily consist of external capacitors connected to the crystal resonator, forming a resonant circuit. Key points. Crystal resonator. The crystal resonator, typically made of quartz or a similar piezoelectric material, is the primary frequency-determining component in a crystal oscillator. The physical characteristics of the crystal, such as its cut, thickness, and orientation, determine its resonant frequency. External capacitors. External capacitors are connected in parallel with the crystal resonator to form a resonant circuit. These capacitors, often referred to as load capacitors or stray capacitors, help establish the desired resonant frequency by setting the capacitance seen by the crystal.
Resonant circuit.
The combination of the crystal resonator and the external capacitors forms a resonant circuit that determines the oscillator's frequency of oscillation. The resonant frequency of the circuit is determined by the capacitance of the external capacitors and the characteristics of the crystal resonator. Tuning and adjustment. By adjusting the values of the external capacitors, the resonant frequency of the oscillator can be fine-tuned or adjusted within a certain range. Tuning the capacitors allows for precise control over the oscillator's frequency, enabling it to meet specific frequency requirements. Crystal characteristics. The resonant frequency of the crystal resonator is primarily determined by its physical dimensions and properties, such as its cut and thickness. Different crystal cuts and orientations result in crystals with different resonant frequencies and stability characteristics. Frequency stability. The stability of the oscillator's frequency is influenced by factors such as temperature variations, aging effects, and external disturbances. Temperature-compensated crystal oscillators, TCXOs, and oven-controlled crystal oscillators, OCXOs, are designed to mitigate frequency drift and provide higher stability over temperature and time. Selection and matching. The values of the external capacitors are selected based on the characteristics of the crystal resonator and the desired operating frequency. Capacitors with tight tolerances may be used to ensure accurate frequency control and matching between oscillator circuits. Frequency-determining components, in conjunction with the crystal resonator, play a critical role in determining the frequency accuracy and stability of crystal oscillator circuits. By carefully selecting and tuning these components, precise frequency control can be achieved, making crystal oscillators essential in various electronic applications requiring accurate timing references. In oscillator circuits, biasing components play a crucial role in establishing the operating conditions for active elements like transistors or operational amplifiers. These components provide the necessary DC voltage or current levels to ensure proper functioning and linear operation of the active devices, enabling stable and reliable oscillations. Key points. Purpose. Biasing components establish the DC operating point or bias point for active elements in the oscillator circuit. They ensure that the active devices operate within their linear regions, minimizing distortion and ensuring stable operation. Types of biasing components. Resistors. Resistors are commonly used in biasing networks to establish DC voltage levels or current paths in the circuit. Capacitors. Capacitors may be employed for AC coupling or bypassing in biasing networks to block DC and pass AC signals. Diodes. Diodes can be used for temperature compensation or voltage reference purposes in biasing circuits. Biasing networks. These networks consist of combinations of resistors, capacitors, and sometimes diodes configured to provide the desired biasing conditions. Common biasing configurations. Fixed bias. In a fixed bias configuration, a DC voltage or current is applied directly to the base or gate of a transistor or amplifier stage. Emitter bias. In bipolar transistor circuits, emitter biasing involves applying a DC voltage to the emitter terminal relative to the base. Collector feedback bias. This configuration uses a resistor divider network to provide feedback from the collector to the base of a transistor, stabilizing the bias point. Self-bias. Also known as voltage divider biasing, this configuration employs resistive voltage dividers to establish the bias point without the need for external biasing components. Voltage regulator bias. Voltage regulator circuits may be used to provide stable DC voltages for biasing purposes, ensuring consistent operating conditions. Stability and linearity. Proper biasing is essential for maintaining stability and linearity in oscillator circuits. Biasing components must be carefully chosen and configured to ensure that the active devices operate within their specified parameters over variations in temperature, supply voltage, and component aging. Temperature compensation. Biasing networks may incorporate temperature-sensitive components like diodes to compensate for variations in temperature that can affect the performance of active devices. Temperature compensation techniques help maintain stable biasing conditions over a wide temperature range, enhancing the oscillator's frequency stability. Adjustment and tuning. Some oscillator circuits may include biasing components that can be adjusted or tuned to fine-tune the operating conditions of the active elements and optimize the oscillator's performance. Biasing components are integral to the proper operation of oscillator circuits, ensuring that active devices operate reliably and consistently over various operating conditions. By establishing stable biasing conditions, these components contribute to the stability, linearity, and overall performance of oscillator circuits. The output stage in an oscillator circuit is responsible for delivering the oscillating signal generated by the oscillator to the load or external circuitry with the appropriate voltage, current, and impedance characteristics. It ensures that the oscillator's output signal is properly conditioned and compatible with the requirements of the application. Key points. Function. The primary function of the output stage is to provide the necessary amplification, buffering, impedance matching, and signal conditioning to drive the load or interface with external devices. It ensures that the oscillator's output signal meets the voltage, current, and impedance requirements of the connected circuitry or components. Amplification. In some oscillator circuits, especially those with low output power, the output stage may include an amplifier to boost the signal amplitude before it is delivered to the load. The amplifier may provide additional gain to compensate for losses in the circuit or to achieve the desired output signal level. Buffering. The output stage may include buffer amplifiers or isolation circuits to protect the oscillator from loading effects caused by the connected load or external devices. Buffering helps prevent changes in the oscillator's frequency or amplitude due to variations in the load impedance. Impedance matching. Impedance matching components, such as transformers, impedance matching networks, or output matching networks, may be employed to ensure maximum power transfer between the oscillator and the load. Matching the output impedance of the oscillator to the input impedance of the load minimizes signal reflections and improves signal transmission efficiency. Signal conditioning. The output stage may include filtering, shaping, or modulation circuits to condition the oscillator's output signal according to the requirements of the application. Filtering components may be used to remove unwanted harmonics or noise from the output signal, while shaping circuits may be employed to adjust the signal waveform or duty cycle. Protection. Output stage circuits may incorporate protection mechanisms, such as overvoltage protection, current limiting, or short circuit protection, to safeguard the oscillator and connected components from damage due to fault conditions or external disturbances. Driver circuits. In some oscillator applications, especially those driving reactive loads or long transmission lines, specialized driver circuits may be used to provide the necessary drive strength and signal integrity. Driver circuits ensure that the oscillator's output signal can overcome the capacitance, inductance, or resistance of the load and maintain signal quality over long distances. Output types. The output stage can deliver various types of signals, including sinusoidal, square wave, pulse, or modulated signals, depending on the oscillator's configuration and the application requirements. The design and implementation of the output stage are critical to the overall performance and reliability of oscillator circuits. By properly conditioning and delivering the oscillator's output signal, the output stage ensures seamless integration with external devices and optimal operation in a wide range of applications. The power supply in an oscillator circuit provides the necessary electrical energy to drive the active components and maintain stable operation of the oscillator. It converts the input voltage from an external power source into the required DC voltage levels for the circuit's operation. The power supply ensures that the oscillator receives clean and regulated power, minimizing noise and fluctuations that could affect its performance. Key points. DC voltage regulation. The power supply regulates the input voltage from the external power source to provide a stable DC voltage output to the oscillator circuit. Voltage regulation ensures that the oscillator operates within its specified voltage range, preventing variations in supply voltage from affecting its performance. Voltage conversion. The power supply may include voltage conversion circuitry, such as voltage regulators or DC-DC converters, to step up or step down the input voltage to the required level for the oscillator circuit. Voltage conversion is necessary to match the voltage requirements of the oscillator with the available power source. Noise filtering and filtering. The power supply may incorporate filtering components, such as capacitors, inductors, or ferrite beads, to suppress noise and ripple in the output voltage. Filtering components help ensure a clean and stable DC voltage supply, free from high-frequency noise or fluctuations that could interfere with the oscillator's operation. Decoupling capacitors. Decoupling capacitors are often placed across the power supply rails to provide local energy storage and filtering for the active components in the oscillator circuit. Decoupling capacitors help stabilize the power supply rails and prevent voltage fluctuations caused by rapid changes in current demand from affecting the oscillator's operation. Voltage regulation. Voltage regulators, such as linear regulators or switching regulators, are commonly used in oscillator circuits to regulate the output voltage and maintain a constant voltage level under varying load conditions. Voltage regulation is critical for ensuring stable oscillator operation and preventing voltage variations from affecting the oscillator's frequency or amplitude. Current limiting and protection. The power supply may include current limiting circuitry or overcurrent protection to prevent excessive current draw or damage to the oscillator circuit in the event of a fault condition. Current limiting and protection mechanisms help safeguard the oscillator and connected components from damage due to short circuits or overload situations. Input voltage range. The power supply should be designed to accept a wide input voltage range to accommodate variations in the external power source or supply voltage fluctuations. A wide input voltage range ensures compatibility with different power sources and enhances the oscillator's versatility and reliability. Efficiency and heat dissipation. The power supply should be designed for high efficiency to minimize power loss and heat generation, especially in battery-powered or energy-efficient applications. Efficient power supply design reduces energy consumption and prolongs battery life, making it suitable for portable or low-power oscillator applications. The power supply is a critical component of oscillator circuits, providing the necessary electrical energy to sustain oscillations and ensuring stable and reliable operation. By delivering clean and regulated power to the oscillator, the power supply plays a key role in maintaining signal integrity and performance in a wide range of applications.